Hello, and welcome to another Algebra 2 lesson. This is lesson 9.5, our objectives: graph tangent, cotangent, secant, and cosecant functions. Describe and understand characteristics of their graphs. We're going to start with tangent. Graph y equals tangent x. Looking at your unit circle, find the tangent value of negative pi over 2 and all of these others. I'm going to start with 0. Tangent of 0. Looking at your unit circle, remember that tangent is y divided by x if you're using the coordinates from the unit circle. So the tangent of 0, this is the point 1, 0. Y divided by x would be 0 over 1. For pi over 6, the next spot on the unit circle, we have rad 3 over 2 and 1/2 as coordinates of the points. So it is y over x. Tangent of pi over 6 equals 1/2 divided by rad 3 over 2. So if you have your unit circle worksheet handy that we did previously, you have most of these answers already on there. You could use that. Multiply top and bottom by 2, cancels out the 2, so we get 1 over rad 3. Simplify it by multiplying by rad 3 over 3, and we get, rad 3 over rad 3, we get rad 3 over 3 for a final answer. So that's for pi over 6. Pi over 4, you are dividing rad 2 over 2 by rad 2 over 2. Any number divided by itself is 1. And keep going. All right, remember, once you figure out 0 to pi over 2, that first quadrant, all of the numbers after that are just going to get repeated, but the signs will change. So for 0, you get 0. Pi over 6, we get rad 3 over 3. Pi over 4, we're dividing rad 2 over 2 by itself, so we get 1. For pi over 3, we get rad 3 over 2 divided by 1/2, so we just get rad 3. And when we get to pi over 2, we're up here on the unit circle. That is the point 0, 1, so that is 1 divided by 0. And what's 1 divided by 0? That's undefined. So we put in undefined here for pi over 2. So once you finish that little section, then you're just reusing those same numbers again. But the signs change. So that's your first quadrant. When we get to 2 pi over 3, we're at negative rad 3, then negative 1. Fill in your table. Rad 3 over 3, 0. Rad 3 over 3, 1. Rad 3, undefined, and then back to negative. And then over here, negative pi over 2 is undefined. Negative pi over 3 is negative rad 3. The next one's negative 1, and then a negative rad 3 over 3. So since we're going to graph these, we need some decimal approximations. Square root of 3 divided by 3 is about 0.6. I'm just going to round to tenths place because we're going to be estimating on a graph. And then the other one we need an approximation for is rad 3. Square root of 3 is about 1.7. So every place we see a rad 3, this one's negative, so that'll be a negative 1.7 when we go to graph it. This one will be a positive 1.7. This one is a 0.6, and so on. All right, keep these numbers handy. We need to make our graph. All right, I took a picture of this, so now I can look at my picture. Do you need to take a picture? Pause here. And now we're making a graph. Let's start with 0, 0. And we're counting by ones on the y-axis. On the x-axis, we have it labeled, here's pi. Here would be 2 pi would be way out here. Okay, we have to know what we're counting by. So we'll do the marks that are here first. For pi over 4, we're at 1. For pi over 3, we're at 1.7. At 1/6, now I'm backing up, we were at the 0.6. So we're kind of getting a curve here. But then what happens at pi over 2? Pi over 2 is undefined. So that means we can't touch pi over 2. That means we have an asymptote. Now let's do some of those negative ones. The negative pi over 6 was at 0.6. The negative pi over 4 is at -1. And let's see, negative pi over 3, which is less than pi over 2, is at the -1.7. And then at negative pi over 2, it's undefined again. So we need another asymptote through pi over 2. So it's hard to tell. It kind of looks like a line that just stops. But what is actually happening is it's going to get closer and closer and closer. As x approaches at pi over 2, the numbers are going to get really big. And as we approach negative pi over 2, the numbers are going to get really small. And we get a curve that looks like this. And it's going to happen again at 3 pi over 2, where our next undefined one was. And what was our number at pi? Our number at pi was 0. And if we do the points on either side, let's get our negative ones and ones in there. At 3 pi over 4, we were at -1. At this one, we're at +1. And we end up with another curve like the first one. So it's another periodic function. It repeats. So that's what happens at those undefined lines, is we get asymptotes. So there's our graph of y equals tangent of x. Notice it goes through the origin. It goes through 1, 1. It goes through 1, -1. Those are really important points that we're going to use when we make our new graphs. And then here, we have that down 1 and an up 1. Those are going to be our important points we're going to use. Okay, let's talk about that undefined part, that asymptote part, a little bit more. Exploring tangent and cotangent functions. The graphs of tangent and cotangent functions are related to the graphs of the parent functions, which are graphed below. Pi over 2 is about 1.57. 1.571. So when we get to negative pi over 2, tangent is undefined. So what about when we get close to it? How about -1.5? If you do that on a calculator and find tangent of -1.5 in radian mode, we have to be in radian mode, we get -14.10. If we put in -1.57, we get -1256. So as we're approaching that negative pi over 2, where is it? Here's negative pi over 2. This dot zooms off to -1256. So it gets really big really fast. So it's approaching negative infinity. And as x approaches positive pi over 2, tangent of x approaches positive infinity. So that's the other direction. Notice at 1.57, which is just slightly less than pi over 2, we're all the way up to 1256. Remember that tangent of x is equal to sine of x divided by cosine x. So tangent x is undefined for x values which cosine of x equals 0. So we learned how to graph cosine and sine previously. So wherever cosine would have been 0, that's our asymptotes for our tangent function. Cotangent. Cotangent is the reciprocal of tangent. So it's cosine divided by sine. So now that sine is in the denominator, cotangent x is undefined for x values at which sine of x equals 0. So that means their asymptotes are in different places. The graph has asymptotes at these places, at the y-axis, at pi, at 2 pi. And notice the curve goes the other way. So it's going from left to right, it's going down to the right, where tangent was going up to the right. Tangent is going up to the right and is centered on the y-axis. Cotangent goes between 0 and pi and goes down to the right. One period of cotangent is pi. One period of tangent was also pi. Characteristics of these two graphs. The functions tangent x and cotangent x have the following characteristics. The domain is all real numbers except odd multiples of pi over 2. At these x values, the graph has vertical asymptotes. The domain of cotangent x is all real numbers except for multiples of pi. That's where the asymptotes are. The range is all real numbers, so they don't have a maximum or a minimum. The period of each graph is pi. This is really important. With sine and cosine, the period was 2 pi. With tangent and cotangent, the period is pi. And then they give you a list of where the x-intercepts occur. Period and vertical asymptotes of y equals a times tangent of bx and y equals a times cotangent of bx. The period is pi divided by the absolute value of b. And then we have some equations for vertical asymptotes. You can use those if you'd like to. I usually don't. We absolutely must have this though. Tangent is centered on the y-axis. Cotangent goes from the y-axis forward 1 pi. Graphing a tangent function. Remember, a tangent function is going to go up to the right and be centered on the y-axis. Describe the graph of g as a transformation of the graph of f of x equals tangent x. So we have two transformations. We have a 2 and a 3. Let's talk about those first before we make our graph. What does the 2 do? Vertical stretch by 2. And what about the 3? What does the 3 do? Horizontal shrink by 1/3. Remember to do the reciprocal. Okay, there's our transformations. Now, we need to figure out the new period of this function. Remember, the period is not 2 pi over b. It is now pi over b for tangent and cotangent. B is 3, so pi over 3. The period is pi over 3. So from one set of curves, from here to here has to be pi over 3, so we need to go forward half of that. What is half of pi over 3? Half of pi over 3 is pi over 6. So these marks have to be labeled pi over 6 and negative pi over 6 because we need this distance to be 1 period. Okay, our graph is going to be centered here. This is not really an amplitude, but kind of. It is not officially an amplitude, but we are going to use that number. With the tangent graph, we go over 1, up 1, And then we can make that curve and we go over 1 this way and down 1. But we're going to go over 1 unit. Oh, 4 sections, just like we did for sine cosine. We're going to break 1 period into 4 sections. So we're going to go forward 1 and up, not 1, but 2. And go back 1 and down 2. We need to draw our asymptotes. And then our curve. As a general rule, if you're making your own graphs, you should draw 2 cycles. So we need 1, 2, 3, 4 more sections that are about that same length. 1, 2, that's where our next x-intercept is going to go, and then 2 more to get to our next asymptote. Every 2 marks was pi over 6, so that's 1/6, 2/6, 3/6. So 3 pi over 6 would be pi over 2. And then make your dots over 1, up 2 from here, back 1, down 2, and draw your curve. Remember, tangents go up to the right. And there's our first tangent graph. There's example 1. Example 2, graph cotangent 1/2 x. We only have 1 transformation this time. So what kind of transformation does that 1/2 give us? Stretch or shrink? It's a horizontal stretch by, the reciprocal of 1/2 is 2. All right, let's figure out the period. Period for tangent and cotangent is pi divided by b. It's a horizontal stretch, so we're going to stretch it out horizontally. Pi divided by b. b is 1/2. So dividing by 1/2 is the same as multiplying by its reciprocal. So it's 2 pi. Now, cotangents are actually easier to graph because we're going to go forward and make a mark that is the length of 1 period. So that's 2 pi that way. And we're going to go 2 pi this way. But that's our 2 cycles already. So our asymptotes for cotangent, if it hasn't had a phase shift, which we haven't gotten to yet for these, that's one of your asymptotes. Because it's going to go from there forward. Okay, we need that in 4 sections. Cut it in half, cut it in half, cut it in half. There's our middle point, but we don't go up to the right, we go down to the right. So over 1 this way, up 1, over 1 this way, down 1, so that our curve goes down to the right, because it's a cotangent. And then we do the same thing over here, so we have 2 cycles. And there's our cotangent graph. So the 1/2 changed the period. Characteristics of secant and cosecant. Okay, changing gears. We did tangent and cotangent. Tangent was centered in on the y-axis. Cotangent shifted forward and went down to the right. Secant and cosecant. Let's find out what these look like. The domain of secant is all real numbers except for odd multiples of pi over 2. At these x values, the graph has vertical asymptotes. Okay, more asymptotes. The domain of cosecant is all real numbers except for multiples of pi. At these x values, the graph has vertical asymptotes. The range of each function is y is less than or equal to -1 and y is greater than or equal to 1. That's weird. So it's got to be less than -1 or higher than +1. So it can't be between 1 and -1. So the graphs do not actually have amplitude. The period of each graph is 2 pi. Good to know. So the only ones that were 1 pi were tangent and cotangent. Remember secant and cosecant? Secant is the reciprocal of cosine. Cosecant is the reciprocal of sine. The one with the s in the middle is the reciprocal of sine. So they have the same length of a period as sine and cosine do. Here's what they look like. Y equals secant of x is the reciprocal of cosine. Secant of x is undefined for x values at which cosine x was 0. So if you graph the cosine x graph, every time it crosses the x-axis, that's where an asymptote goes for the secant graph. And then for the secant graph, we get these little U-shapes off of the hills and valleys, pointing up off the hills and pointing down off the valleys. And then cosecant, we build that one on sine. Wherever sine x crosses the x-axis, that's the asymptotes for cosecant. And one period is 2 pi. All right, let's give it a try. To graph y equals a times secant of bx, or y equals a times cosecant of bx, first graph the function, cosine or sine, respectively. Then use the asymptotes in several points to sketch a graph of the function. Notice that the value of b represents a horizontal stretch or shrink by a factor of 1 over b. So the period is going to be 2 pi divided by b. Okay, let's look at example 3. 2 times secant x. The first thing we have to do is graph y equals secant is the reciprocal of cosine. So we have to graph y equals 2 cosine x. Once we do that, then we'll draw our U-shaped curves for the secant. What is the period? The period of cosine x is just 2 pi. The amplitude of cosine x is 2. Okay, 1, 2. 1, 2. That's our -2. We need at least 2 cycles, so we'll go 2 pi this direction, and then we'll go to -2 pi in a little bit. But let's break this into 4 sections and get our cosine graph going. So cosine. Cosine starts at the top, comes down. So one with the horns. That's the way the parent function for cosine looks like. So it starts at the top, middle, bottom, middle, back to the top. Let's go ahead and build that other half. We always want at least 2 cycles. So here's our -2 pi. Break it into 4 sections and finish your pattern. Middle, bottom, middle, top. Okay, I'm going to draw this as a dashed line because this is my cosine graph. It is not my cosecant graph. Fill in your asymptotes. Your asymptotes are wherever the cosine graph crosses the x-axis. And now we will draw our secant graph. So off the top of this hill, I'm going to draw a U-shaped curve. we'll get some down here too. This one we could draw half of it. You draw half of it. And these are your cosecant curves. 2 times secant x. There it is. This was our little cosine sketch. Okay, that's example 3. Example 4. Graph a cosecant function. All right, cosecant is the reciprocal of sine. What does sine of x look like? Does it start in the middle or does it start at the top? It starts in the middle. We get a hill and then a valley. Okay, we need to figure out the period. We have an a of 1/2. We have a b that is pi. The period then is 2 pi divided by b. So the period is 2. Now we can start making our graph. We are graphing a sine curve. Break that into 4 sections. There's 1, but our amplitude of the sine is 1/2. So it's going to be a pretty squished curve. Sine starts in the middle, top, back to middle, down 1/2, back to middle. Okay. Draw it on the other side. Draw your asymptotes. Your asymptotes go wherever that sine curve crosses the x-axis, because division by 0 is undefined. And then draw your U-shaped curves for your cosecant graph. Goes up off the top ones and down off the bottom ones. And up off the top ones and down off the bottom ones. And there's our cosecant graph. And that's example 4. Tangent cotangent dance. Did you know there's a dance? You ready? Stand up. Okay. Tangent. I'll turn around. Tangent goes up to the right and is centered on the y-axis. And then step forward, so off to the side to the right, so forward on a graph. And then switch your arms, cotangent. Back to the middle, switch your arms, tangent, cotangent, tangent, cotangent, tangent, cotangent, tangent, cotangent. Do the dance. All right. Don't forget that you have to shift forward for cotangent. Only tangent centered on the y-axis. Cotangent is all in front of the y-axis. All right, start your big ideas assignment, 9.5. Thanks for watching.